If I could have your attention, ladies and gentlemen, please. As many of you know, Chris Hughes, who was our branch secretary, sadly passed away in April. Chris was born in June 1954. To acknowledge what a key figure Chris was in the branch, future June lectures will be named the Chris Hughes Lecture. When possible, the lecture will be STEM or rotorcraft related, subjects that Chris had a great interest in. And thank you to Robin and Tom, two of Chris's children, for being here for this, the inaugural lecture. Chris was a society member for over 52 years and served in various branch roles for over 30 years, including as branch secretary and branch president. He showed a huge commitment to the society, running STEM events, introducing lectures, providing insightful summaries and votes of thanks, and regularly attending branch's conference. Chris was a great advocate and active supporter of STEM projects. When the Aero Society and Boeing School Build a Plane Challenge was announced, Chris was instrumental in obtaining not just one but two kits for local schools. Erklewood and Ormiston Newer schools, with supervision from branch volunteers, built the aircraft to a very high standard. Those two Rand's Coyotes are amongst very few microlights to be displayed at Farnborough, and the volunteers also helped complete a third aircraft. After the Build-A-Plane aircraft were complete, Chris mustered many of the team to start the STEM High Flyers charity to build the Sherwood Ranger with local schools. He emphasised that the aircraft were a by-product of showing the students engineering as a subject, teaching practical skills and enhancing soft skills such as teamwork and resilience. He had an unshakable belief in the projects, based on practical experience and examples, where young lives were seen to change for the better. The STEM High Flyers project kicked off in 2019, the same year Chris was diagnosed with cancer. It says a lot about Chris that treatment sessions were often moved to fit around STEM commitments, and that while at the local hospice, he was planning to use teams to present on the aeroplane build projects at last week's branch's conference. Chris spoke on STEM subjects and attended careers fairs at local schools and was able to engage all ages from year 1 to 6th form. Chris was hugely effective in the branch. He had ambitious ideas, which his formidable intellect and hard work turned into impressive achievements of the highest standard. Thank you for attending this, the inaugural Chris Hughes Lecture. I would now like to ask Darren to introduce our lecturer for the evening.
Thanks, Chris. Good evening, ladies and gentlemen. To introduce our speaker tonight, Paul Withey is currently Professor of Casting Technology at the University of Birmingham. He's been working in the field of casting with a specialism in single crystal casting for 3 decades. The majority of this time as a casting specialist at Rolls Royce Aerospace, primarily focused on turbine components. I believe Paul is setting a record for us tonight, as in we've had multiple speakers over the years, but I think Paul is the first person that's had 2 lectures in 1 season. Last time, if you were here for the brilliant comment lecture, he gave that one, but tonight he's going to tell us why jet engines don't melt. Thank you. Paul.
Thank you very much. Darren warned me the 2 things not to do with playing with the mic, so we'll try that one.
Yeah.
Hopefully you can hear me. And playing with the lights, so we'll see how that one goes if I do that and that. And there's a good reason for doing that one. Really good. Little think about it, I'm sure. Yeah.
They're going.
They're going.
The
Right.
other thing.
What I will do though, maybe in a bit, just try that one. Right then. So why don't jet engines melt? And my career has been based, as Darren's kindly pointed out, for 3 decades, around single crystal casting. Now, a lot of the talk was written around aircraft, commercial aircraft. But one thing to remember, and I'll try and touch on this as we go through, rotorcraft became viable. I mean, Leonardo da Vinci designed a theoretical rotorcraft, which was theoretical and man-powered and probably wouldn't have actually got off the drawing board, which is probably the best place to leave it. And whilst they came in with internal combustion engines, in terms of piston engines, they actually became viable with the advent of the gas turbine. The power-to-weight ratio of a gas turbine actually means that you can fly a helicopter in a way that means you can actually carry some load, which was always the way, that's a good achievement. And so everything I'm going to say today about why jet engines don't melt applies to helicopters, civil aircraft, military aircraft, anything that's gas turbine related. And to an extent, power generation, oil and gas pumping, anything that uses a gas turbine. So it's not that most of the examples are picked from civil aviation, because that's where I could nick most of the stuff from Rolls Royce. Sorry, that's on video. But equally, it does actually give a good story to tell, especially for students who are trying to engage in STEM subjects. Now, the talk tonight is going to get a little bit technical, and I can only apologise. I'll try and keep the technical stuff as light and as high level, but if I start getting too technical, just throw something at me and we'll change the subject. Right, so I'm going to try and cover a bit of an introduction. Creep failure, there's the technical bit. The superalloys, so the materials that we make them from, making the blades, and we'll kind of tidy it with that. I will be passing a few bits around. They're kind of scattered there to try and remind me to pick them up and pass them on. So those of you on playing Sudoku at the back, you may need to come forward a bit if you want to, otherwise your colleagues are going to be straining to pass them. I'm going to pass them to the front row, and hopefully by the end of the lecture most things will have got somewhere towards the back. But we'll see how it goes. Aviation development. Right. It is a long time ago. It's not that long ago that the Wright brothers made that first powered flight. So actually the development of aviation has been really, really quick, and I'm sure you're all aware of this. And it was only 1952 was the world's first passenger aircraft in the Comet. And that's a picture of the Comet that used to be outside. In 1959, world's first non-stop transatlantic jet service. And most people today assume, popping across the Atlantic is kind of, I just need to pop on and I'll go on the internet, I'll buy a ticket, I'll be there tomorrow coming. And it's all kind of normal. Today's aircraft can carry over 10 times the number of passengers and up to 4 times the distance of that first jet airliner. So since 1952, we've come all that way. But going back, Wright vertical 4-cylinder engine was what the Wright brothers used for that first powered flight. It was designed by the Wright brothers because nobody else made even... If you think, cars weren't that much older than aircraft at this point, 1890s. So when they went, we need a really good power-to-weight ratio motor, everyone went, we haven't got one of those. So they had to design their own. And it was handcrafted, hand-designed, handcrafted by their mechanic, and it's an aluminium casting. They actually got a foundry to do an aluminium casting, first use of aluminium in jet engines, to make the cylinder block. And they made the cylinder block, and it had 12 horsepower, and with the power of the propeller, about 90 pounds of thrust. We'll come back to these kind of numbers later. But 12 horsepower. If you had 3.5 of them, you could power a Reliant Robin. So I wouldn't say that that they had what they needed for that first flight, but it wasn't very powerful. And what we've done since then is we've made it to the point where we can get people across the Atlantic, we can get them around the world, we can do long flights. So, seen an incredible development since 1903. Many areas: payload, range, reliability, safety. We don't expect to crash these days. Number of takeoffs, roughly 8 landings. And it's been enabled by developments in many areas, but the casting of aerospace components that we'll be covering today, Professor of Casting kind of was in the clue, it's the casting of aerospace components, old processes have been modified for new materials. So that's where we're going to be going through. But just that concept, the piston engine, that first piston engine and the gas turbine. Why was the gas turbine? It was a steam turbine before, when it was 1800s. Whittle really saw the benefit of that. Otto von Hayne the same. That you get a piston engine. What you're trying to do there is you're trying to generate power from burning fuel. And there's no difference between the two different types. The issue is, in a piston engine, you're going to do everything in the same space. You're going to suck the fuel in with the air mixture. you're going to compress it. You're going to ignite it, get it to expand, then you're going to try and eject it and exhaust it, then you're going to go all around that cycle again. For each of those bits of the cycle, the temperature you need for it is going to be slightly different. And it kind of all comes out in the wash, and your internal combustion engine, your piston engine, runs at a pace that is kind of okay, and the temperature for what it's trying to do, everything all at once. And what's more, we tend to rely on the fact that it doesn't kind of get really, really hot when it's combusting, because actually it would start to need more cooling than we currently use for these type of engines. The gas turbine is brilliant because what it does, instead of having the air in one place and getting it to do everything, is we pass the air down the engine. So it starts at the fan, it gets a bit compressed, and then gets more through the fan, gets a bit more compressed through the compressor, pops out into the combustion chamber, we add fuel, we set fire to it, bit of a bang, chucks it out through the turbine, it starts to expand. We can actually do each of these stages in a line down the engine. By doing it in a line down the engine, we have the benefit that each process can be optimised for what we're trying to achieve. And because we work in aerospace, we're going to really stretch the limits of what we can do. If we can make it work really, really well, we will do. Because power to weight ratio is absolutely key, and fuel efficiency is the total target. If we can do this for less fuel than we could do it a few years ago, we've got a winning product. So where has it kind of started? That was one of the early gas turbines. This is where the show and tell turbine blade, from that. There you go. Modified steel, mnemonic 80. That's what it looked like. And for those of you familiar with gas turbines, this looks much more like a compressor blade than anything else. But that is the first. Everybody's going to argue which gas turbine ran first. That's off a de Havilland Goblin engine, which was actually the one that first powered the Gloucester Meteor, because Rolls Royce engine was late. So it was frame number 5 that flew first with different engines. So, but it's not much different if you look at the Whittle engines. They all look the same, forged pneumonic steel. But you look at what we've got today. Massive things hanging under the wings, large fan. The early ones didn't have the fan. The technology has moved on so much to do what we're trying to do with that technology. And what's that left for thrust? If you look at the early thruster engines, I talked about 90 pounds of thrust for the early Whittle, the Wright brothers engine. That wouldn't even just about make it off the axis today. So you see that kind of 1,000 pounds of thrust. I'm using the old nomenclature, but it goes up like that. Now I stopped plotting this chart a couple of decades ago because it doesn't go up anymore. It kind of flat lines. What's happened is that as we have developed the technology to make these more efficient, we haven't needed bigger and bigger planes. We've kind of maxed out with the plane size, and we've dropped it down from 4 engines to 2. So it's at the point now where you take one of those, the Trent 8115, Trent XWB 97K, those kind of engines that are floating around today, 2 of those would power the early jumbos. So you could strip off 4 engines, put 2 on, and that's more fuel efficient, which is roughly what we've done in terms of airframe design, which is why things like the jumbo jets and the A380s, Airbus A380s are dropping out of service. They've got 4 engines, they're less efficient. We've closed the reliability of the engine has allowed us to close the gaps over the oceans that we used to have with 2 engines, because you're not allowed to fly a long distance on 1 engine. So you had to prove that you could get to your destination or your alternate if you had an engine failure. 4-engined aircraft, no real problem. Fly on 3, you'd fly around the world on 3 if you had enough fuel. 2-engine aircraft lose an engine, you've got to make sure you've got the reliability left in 1 engine to get to your alternate airport or your prime. As we've made the engines more efficient, the amount of time we're allowed to fly on 1 engine has gone out from 1 hour to 1.5 to 2 to 3, and it's gone out. So we're now allowed to fly a long distance, which means that the holes that were over the oceans and what could only be closed by a 4-engined aircraft have completely gone now, which is why the world is dominated by 2-engined aircraft. Also, not many people. You could re-engineer an Airbus A380 for 1,000 people if you so desired. Whether you would want to be on a plane flying long distance with 999 other people in an aluminium can I think it's a debate for the travelling public, but it's doable. So what does it mean in terms of comparative power? Family saloon car kind of sits, there is a line of dots, just about. Tesla, Formula E, Formula One car, Eurostar, we're actually starting to make an impression. Ajax, cute, Queen Elizabeth. Boeing 747 at takeoff, about 130 megawatts of power. So it's a huge amount of power to actually get 350, 400, 450 people into the air, but we do it regularly. So that's the kind of the power that we need because we're trying to lift everything off the ground. So what's happening inside the gas turbine while we're doing that? Well, we're actually compressing the gas, as I said, but we're going to compress the gas to about 60 atmospheres to really squeeze it down, so that when we add the fuel, it's got a lot of energy and it's going to just go out the back, it's going to expand really well. So that pressure chart at the top, you can see it goes to 60 atmospheres through the compressor stages, it goes into the combustion chamber, we add the fuel, it expands, and we blow it through the turbine. Now, in old engines, we didn't have the big fan on the front. We used the fact that there was gas coming out at high speed out of the back, that gave us thrust. Today, 10% of the thrust is coming from that jet. The other 90% is the fact that we put a whacking great fan on the front, and we're actually generating most of the thrust from what is a 3-4 metre diameter propeller set, ducted propeller, and that's what we're doing. But you can take that core, you can take the fan off the front, you can stick it through a gearbox and pop it up to a rotor set. Works exactly the same on a helicopter. Makes no difference to the technology on the inside. And in fact, it does make no difference. We, in Rolls Royce, we make bits for helicopters, military aircraft, civil aircraft, power generation in the same production plant, in the same equipment. Makes no difference to us. It's a component. Helicopter blades, civil blades. Yeah, so helicopter blades aren't that big, but because you do not need 100,000 pounds of thrust to lift a helicopter. You certainly don't mean that big on the back of your helicopter. So we're going to squeeze it down. What that also means is that when we add the fuel and stick it out the back, the temperature goes up. Now, the compressor, adiabatic kind of compression, means that you're going to squeeze it down to a 60th of its previous size, so 60 atmospheres. That puts it up to about 650 degrees C. Just purely compressing the gas. Chemistry tells you that goes to about 650 degrees. So when it goes into the combustion chamber, it's a bit warm. Then we set fire to it, then it comes out the back. Now in a gas turbine, the efficiency of the gas turbine is entirely determined by what happens next. And the components that sit directly behind the combustion chamber determine the efficiency of the engine, so the engine cycle itself. The fan on the front determines the overall thrust and to an extent the noise, but all of the things like emissions, efficiency, everything else comes out of the turbine section, and primarily the high pressure turbine blade, which is the first rotating component behind the compressor. And that's because that gets hit with the highest temperatures, so it has to be able to survive as best it can in a really, really aggressive environment. So the temperature peaks out, and then as we expand the gas through the back end of the turbine, and the turbine is just designed to take power out of that gas stream to power the compressor at the front. So all we're doing is we're taking power out of the back, whipping it up to the front to make it all turn, to suck more air in to make it go again. And the fact that we've put fuel in and we've added fuel to it means that we've got an energy balance which generates thrust at the same time. So we get the energy of the fuel, the chemical energy is turned to motion, thermal energy, and then onto kind of mechanical energy. So, behind the combustion chamber, we've got in red the high pressure turbine blade. And that's the bit that determines your engine cycle. And that red component is followed by the yellow one, which is another turbine blade in a Rolls Royce engine, the intermediate pressure turbine blade. That powers a different compressor set. And then the low pressure is in blue. Now it gets cool. So we're starting here at this hottest. By the time we're down at this back end, we're probably exiting the gas turbine at about 700 degrees C. So that's the kind of the temperature drop as we drop through the engine. So those are the components that are absolutely crucial. That one in red is the one I'm going to focus on today, because that's the one that drives everything. And what we've done over the years, we've just driven that temperature up We would like it to get to about 2,200 degrees C, maybe a bit more, and then burn the fuel as hot as we can to make it as efficient as we can as a kind of a thermal engine. 2,200 degrees C will melt most things. There aren't many things around that you'd want to make a turbine out of that will survive that. So currently we're up at about just over 1,600 degrees C. Now 1,600 degrees C is a bit of a challenge because a lot of that temperature is going to have to be either absorbed or removed from the system, or we're going to have to deal with a lot of heat. And we're going to try and make sure that that engine doesn't melt. And 1,600, 1,608, 1,610, which is roughly where we are, is probably going to take a lot of technology to keep us there. I'll kind of run through some of the numbers. The blade that's been passed around, the Withey one, that took about 800 degrees C. Straight steel derivative, it got a bit warm, but it was fine. But also, we didn't expect it to last more than about 100 hours before we stripped the engine down and swap it out. So there wasn't we didn't ask it to do a lot of flying. Because when you talk about the Trent turbine blade, and this is going to be the same, it doesn't really matter if it's Trent or any of the other manufacturers, you're going to do this to it. It's going to withstand a gas stream of 1,600 degrees C. That's more than 300 degrees C above the melting point of the metal. It's about 600 degrees C, 550, 500 degrees C, above the point that the metal goes a bit soft. So you've got a massive temperature gap between the point where you want to operate. So next time you fly, don't sit there and go, oh, the blade's out there, they're seeing 500 degrees C above where they should be. You'll rattle the poor person sitting next to you thinking they're going to make it to wherever you're flying. And by the way, people keep asking me for mind flying. I don't mind flying. I know what goes into some of this stuff, so I don't mind it, but you don't want to think about it too much. We're going to rotate these blades at 13,000 RPM because we need to spin them in the gas stream. That's the equivalent of taking one of these blades. There you go, one of these blades. And if we grabbed it by the root and hung a lorry or a bus off it, it would be about the same weight. Now there's 60 odd of these in a set. And what we're going to say is we're going to hang it by that. And every blade has got a bus hanging off it statically. We're going to spin it that fast that this root block has got to take those kind of loads. It's about 18 to 20 tonnes. It'll keep us quiet for a bit. Hang on, tell you what I'll do. Oh, yes, I will. I'll start at this side, you can kind of pass them back in bits. Right, so, that's a few £1,000s worth of spares. So anyway, rotating at 13,000, so we're putting a huge load on these. We're not expecting them just to kind of spin naturally. The heat transfer rate, so to keep it down at 1050, 1100 degrees C, the heat transfer rate that we're going to have to take the heat out of that system, that one blade, so I'm just talking about one blade here, is about the same as taking all of the radiators in a 3-bed semi and cramming them into something the size that I'm just passing around. So it's that kind of heat transfer rate that you're expecting it to happen. So we're having to dump the heat somewhere. But we also expect it to power the compressor, the high pressure compressor, and pull more gas in and compress it. 900 horsepower, each of those blades, 60 odd in a set, 60 plus, more than 60 in a set, each one has to generate more than 900 horsepower. So when we spin up one of these engines for takeoff, it's the same power as 3 Grand Prix at once. In terms of if it was an internal combustion engine and we were just kind of enjoying the sport of it. So it's a lot of power in a gas turbine. 900 horsepower is about the same as a Formula 1 car. And actually they've kept pace. Formula 1 car versus turbine blade power has kept pace over the last couple of decades. We use cooling air. You'll see there's holes in it. We blow cooling air in and we pass it around the blade to allow us to deal with that heat. And you can see the shapes of the cooling passage, and we're going to blow it in. Now, the problem is that if you're going to blow air in, it's got to go out through the film cooling holes. We can't have hot gas coming back in through the holes, we've got to blow out. The only place we can find high pressure air that's higher than the gas stream it's sitting in is from the back of the high pressure compressor. So as I said earlier, it's about 650 degrees C by the time it gets there. We bleed some of this off, pass it through the turbine blade. So, I've had a career of this. You walk into the design teams and they say, oh yes, we've got cooling air. Yeah, cooling air. What temperature is your cooling air? It's 650 degrees C. Don't use it in your fridge. You know. The concept of cooling, just because we're operating at 1600 degrees C, 650 is cooling. But it's not, you have to get your mind around the fact that it'll still melt stuff. So we've got this cooling air, 650 degrees C, we're passing it through to try and keep ourselves at about 1050 degrees C in a gas stream of 1600. So that's the thermodynamics. That's fine, but then we've got customers. And the fare-paying public really appreciate the high tech that we go to put into these engines and the costs that are involved in making it, so they look for the cheapest flight they can. So the airlines want the cheapest option that they can get. Or, put it another way, can you do 10 million flying miles between services? 10 million flying miles is quite a distance. An aircraft, once it's launched, we won't expect to see it for another few years, 5, 6 years, before it comes in for its first service. Oh, and by the way, just like everybody looks after their car and polishes it, airlines, they leave the aircraft outside on the stand, they let it get rained on, it gets hit by lightning once a year, it gets covered in all sorts of nasty chemicals when they're de-icing it. They really don't look after these things. And by the way, it ingests all sorts of stuff down the runway. So we are not looking after these things, but we need 10 million flying miles, guys. So we've got to make it robust and high-tech. Customers, it'd be a lot easier if we just focused on the technology. So what we've got, that jump, you see, 1960s-ish, Conway engine came in, we started using cooling air. Actually, the Germans, 1943, used cooling air in the Junkers Jumo 002. They couldn't get the alloying elements for the steel, so they used cooling air. They used forged tube, blew cooling air through it, and the engine worked a treat. But because they didn't win the war, and the engine got canned, we went back to using forged steel-type blades, and didn't actually start using cooling air again until the 1960s. But then we brought it back in again, the Conway, and so we started using cooling air, and we saw that jump in temperature. Then we started coating the blades, and you see the white coating on that blade, that's ceramic coating. I'll touch on that right at the end. And that ceramic coating is like a tea coating, and it just gives another 200 degrees. And that's why we've jumped up again. I'll come back to the couple of spots in a minute. Right, creep failure. Sorry, I'm now going to kind of go into what the problem is. And I've covered some of it. We're going to take these blades, we're going to hang 27 tons off them at 1600 degrees C. Now, although it's not all, it's probably 1,050 degrees C. So it's still quite warm for an alloy that melts at 1600 degrees C. But we're going to hang these blades in those kind of temperatures for a long time. And because of that, we start to see something called creep failure. Some of you will probably know it, I guess some of you won't, so I'll kind of run through it. Creep is the deformation of a material under constant load over a prolonged period of time. And actually, some materials creep at room temperatures, others require a bit of a temperature boost to do it. So lead creeps. Which is one reason why cathedrals change their roofs every couple of centuries, because actually the lead roofing starts to move its way down the tile and they fatten up at the bottom. So we start to see creep failures in that. You see creep failures in all sorts of materials at different temperatures. The alloys that we use, it tends to be that we're going to walk into it anything from about 1200 degrees C onwards. So we're fully aware that we have to stop creep failure because we're going to hang these things under a fairly constant load. And that's a standard engineering's graph that shows it takes a while to get going, then it's steady state creep, and we try and make sure it's steady state creep for a long time, and then you get your final failure. Now, creep in metals happens for a number of different reasons. Diffusion creep, so you get little imperfections in the crystal, you hang it up, because of the stress direction, these imperfections can move around. It requires high temperatures, but you get these moving around, and so they hit the grain boundaries, and then the grain boundaries go over, and you get that. Grain boundary sliding, which is where the grains of, if you look at a standard metal, and polish back a standard metal, it looks like a sugar cube. I'll pass them around in a minute that you can look at. Lots of different grains in different orientations, but because those grains, if you kind of take a sugar cube and try and break it, you're not breaking the individual grains of sugar much, you're actually breaking the boundaries between the grains, because that's the weak spot. And so those grain boundaries slide in metals. And it's that sliding that means that you get creep. And so we get elongation with time. So when we start off with a blade this long, it grows with that stress in that direction, it grows and grows. And the longer we leave it, the more it grows. Until the point where we say you can only have so much, and then we scrap it out. We only so much growth. Dislocation creep, atomic defects, so dislocations in the crystal, so imperfections in planes of crystal atoms. You can see them on some high-power microscopes. And you can see these, and they move with time. So lots of atoms moving around is why we're trying to stop this happening. It's all creep, but it's really on the atomic scale. So what we can do to stop it, and this is the metallurgist kind of go-to list of things to do, we can avoid plastic deformation by cold working. Now, I guess many of you have taken a piece of copper pipe and you bent a piece of copper and bent it one way, then found out that you can't bend it back again. Yeah, it bends. What happens is, a lot of these dislocations move, they tangle up, they toughen the material, it becomes harder. And actually, that means it's much tougher to creep as well. So if you put in loads of dislocations, you actually you tangle them up and they don't move very well and they all stop moving. That slows creep down. That's one way of stopping creep. Refining the grain size, larger grains, less creep, fewer grain boundaries. Fairly simple. Solid solution strengthening, which is a favourite one. Adding another element to deform the crystal lattice. So you find an element that you can stuff into your alloy and won't come out as a precipitate, but it just kind of goes in there in a solution and it kind of deforms the crystal and the dislocations meet it, these atomic imperfections meet it and get stuck. And there's precipitation hardening, where we actually try in the metal to get different phases to pop out when we heat treat it at the right size to tie up these dislocations, these atomic imperfections as they move around. That's the kind of metallurgist handbook for creep. And there's a number of textbooks written about that, and that's the way we stop creep. Now, we employ we employ 3 of the 4, and I'll come back to the 3 in a minute. Now, if we're going to look at that, what alloys would you pick for these kind of temperatures? Nickel chrome solid solution alloys have inadequate strength. So some of the historic alloys that people have picked haven't got the right strength. They're just not, they wouldn't be strong enough for gas turbine use. Good for creep, but not at these kind of loads. So blocking of dislocations and grain movements required. So we could carbides. Carbides, we've used those for centuries. It's why steels, put a bit of carbon in there, you get carbides, you start to tie, you get steel's much stronger than that. Iron, we learnt that through the Industrial Revolution. Really, really good. Unfortunately, you go over about 600 degrees C and those carbides start to coarsen, at which point you lose strength. So we're kind of limited. We're a few hundred degrees C above where that actually works for us. So we actually use a nickel aluminium alloy and we get little precipitates that we can control at the right temperature. I'll show you some pictures of something in it. But just to go on to that, the superalloys, these are the blade. These materials that I'm going to pass around are made out of what are called superalloys. They're called superalloys. I don't know who gave them the name. They don't go around kind of capes. Anyway, they're called superalloys because they retain their strength to about 80% of their melting point. And actually, it's crucial that they do. We're going to really squeeze the last little bit of juice out of these materials. And so the fact that they can go to about 80% of their melting point and still be a useful material, somebody went and coined the phrase superalloys. It may have been Chesterton in the States, I'm not sure. Whoever it did, they'd been reading too many Marvel comics. So, 3 kind of classes of them: nickel-based, nickel-iron base and cobalt-based. We tend to be focused only on the nickel-based. Nickel-iron base haven't quite got the strength. Nickel-cobalt, a bit too heavy, equally strength-wise. But then we're going to stick in other things to kind of, it's not just nickel, we're going to stick other things in there as well. And I think I've spent too long being a metallurgist. We will throw the kitchen sink at these things if we think it will work. It's not that we're going to add 1 element. Why add 1 element when you can find 10 in the periodic table? So we're going to see what some of these elements do for us. But nickel itself, current spot price isn't far off $17,000 a tonne. Bulk of the use is austenitic stainless steel, boiler plant and cutlery. So nickel's really got a place in the world doing stuff anyway, even before we got involved. Nickel plating, 16%, so jewellery, plating, things like that, nickel coatings. High nickel alloys, 12%, nickel alloy steels, another 12%, and then bits and pieces. So it had a career before we took it on. Now it's being used heavily in the aerospace industry. It's a cubic alloy, I'll come on to what that means. The issue with nickel alloys, and this is where it gets horrible, density 8.9 megagrams per litre, or 9 tonnes per cubic metre. So kind of would be 9 tonnes of weight. Not an ideal aerospace alloy. When you talk about aerospace alloys, people go titanium, aluminium. Great, low density, high strength. Nickel, not so much. Titaniums won't work, by the way. They go through a phase change, going up the alpha to beta phase change about 880 degrees C. That means that you can't use them much above 400 or 500 degrees C without having a phase change in service, which weakens the whole system and the whole thing goes to pieces. Which is why we don't use titaniums. It just doesn't work. Nickels don't have that phase change. They don't change structure halfway through your process. Right then, so back to that slide. 4 methods of avoiding plastic deformation. Cold working, which I said was great. You know, bend things, tighten the dislocations, works a treat. Problem is, you get out of that fix by heating it up. So if you ever bent your copper pipe and found out that you really need to bend it back, if you heat it up, you can then bend it back again because the heat kind of fix the dislocation tangles and it's sorted out the atoms, they've all diffused, sorted out the crystal structure, you can bend it back again. Job's a good one. The problem is if your service temperature means that even if we took a turbine blade and beat it up before we put it in, by the time it had done its first engine run, it would have sorted itself out and we'd have fixed the problem. And what you don't want to see is after every flight, a maintenance fitter going in with a hammer and bashing the engines, because that's not a good look if you're trying to fly. So we don't use cold working. The other 3, however, we're going to have a pretty good go at. We'll start at the bottom. Precipitation hardening. Having a second phase to tile dislocations. It's been used for years. Steels, aluminium alloy, we've done it for centuries. Nickel, we're going to really push the boat out. Sorry, phase diagram. I realise this isn't everybody's cup of tea. But effectively, we're going to add aluminium in there, and we're going to start with aluminium goes into nickel, and it goes into solution initially. So it basically disappears into the nickel mix, and it's fine, up to about 10-20%. And you wouldn't know it was there. It lightens the alloy, and it just kind of sits there. Above that, it actually forms nickel-3 aluminium. Or aluminium nickel-3 as it's written there. But that's actually a different phase. And it's actually an ordered structure. And then the atoms suddenly start, instead of just sitting anywhere in the crystal lattice, they suddenly get really, really fussy about where they're sitting. And they won't sit next to each other. And so they pick their spots in the crystal and get really awkward. So that's an ordered phase, and that's just a kind of sit anywhere phase. What it does mean is that they come out as a precipitate, but it's called coherent. It's actually exactly the same crystal structure, it's just ordered rather than disordered. It's got a slight mismatch. Maybe it's kind of the spacing of the atoms, but only a few %. So actually it sits there in the crystal lattice, and the atoms themselves think they're in the same crystal. There isn't a boundary. So we can't get sliding because there isn't a boundary that they've noticed. They can wander to the next atom and it just carries on. So that's really nice. We get these ordered precipitates. So that's the technical stuff. What happens is we've got face center cubic, which means it's a particular cubic crystal structure, really good for strength. But then they get fussy, and the nickels sit on the face cubes, the aluminiums sit on the corners because they don't like sitting next to each other. So they all disperse to their corners. As soon as you get to the right concentration of aluminium in there, it splits up, sits in its different places, gives us this coherent precipitate. Now we've got all the metallurgy going, all that's exciting. What can we do with this? So anyway, we've got the aluminium in there. We don't like a lot of aluminium. Aluminium melts at too low a temperature. So we're going to get things that pretend they're aluminium. Tantalum and titanium, really good. Cobalt substitutes for nickel a little bit, but tantalum, titanium and aluminium all pretend they're aluminium. So they sit on the corners, nickel in the face centres, and we've got this coherent phase. The reason it matters, if we took a crystal and we loaded it up, and we just kind of moved a dislocation through over time, we jog down one, just like it shows on down that red line, we end up jogging down one place. No problem, we've loaded it up, added temperature, and the atoms have one by one gone pop, 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 unbonded from its neighbour, dropped down, bonded to the one next door, and the dislocations move through. You do that with one where they don't like being next to each other, and you end up with, oh, if I pop through, now I'm sitting next to somebody I don't want to sit next to, and I don't like that. So you've unzipped the crystal, zipped it back together again, and they're going, I didn't want to be here. So actually, the fix is, let's send through a second dislocation, and you have to move them all along again. So you have to do 2 dislocations to get one happy crystal. And that's basically what happens. You have to send through 2 dislocations. They're called super dislocations because they travel around in pairs. And that's the cubic precipitate. And you can just about make out, if you can kind of squint and whatever long enough, you see there's 2 white lines across there. That's 2 dislocation planes that we've got in that precipitate that's popping out, and we're getting them in pairs. So we can see them, we do know it's right, and we have imaged them. So we aren't just believing our own happy juice, it does actually exist. So we've put a coherent precipitate into there, and as you can see, in most alloys, for any of you that have looked at aluminium alloys or whatever, you get 5% of your material is precipitate, and you've tied up the dislocations and you're really happy. In nickel, we go for 70%. We don't kind of hang around at 5, we just go to ridiculous limits. All of these alloys are generating the extreme kind of alloy chemistry that we can. 70% of it is precipitate. But it's really, really good. What happens is that those partials, they move, sorry for talking about which slip planes they move on, it's not really important, not for this, but they move along, and they move down particular crystal planes, these dislocations, and so as you stretch them, they go around in pairs. The thing is, we get a strength increase at higher temperatures. That's good, because actually it means that we're not dropping off it. Most alloys, when you see them, they go along and then they drop off. Nickel alloys go along and get stronger. That's quite nice. But why? What happens is, as you go up in temperature, alloys get weaker because what happens is you've got these planes that dislocations can move through, these atomic distortions. As you get hotter, they can go on different planes in the crystal. And so they can travel in different directions. What happens if you've got 2 that have to travel together? The best analogy I've got is you've got a train on a track, and they're going around together. All of a sudden, there's a siding goes off, and one of them decides it's going that way. And one goes off on the main line, and one goes off down the siding, at which point they're on their own again, and they're sitting next to the mates they don't want, and they all stop moving again. And so we get strength, as we open up more options of moving in different directions, we actually get a strength increase because they all decide they can't be bothered to move off without their friends. So we have to put even more energy in, hence that little jump. So we really have engineered these materials beyond belief. You can see a lot of words on that side saying why it works. Those are actually TEM images from Roger Reed's book showing that those 2 dislocations travel around together. And we can image them, we can look at them, we can see them moving. And especially if we go for high volume fractions of this precipitate, we actually mean that 70% of the material is precipitate. There's a bit of a philosophical debate about how much do you have to have in there before it stops being the precipitate and becomes the main phase. But we still claim at 30% that the main phase is the main phase. But we get this precipitate that's in there, and we just tie up this dislocation. So as we try and stretch these materials, we get this lovely strength increase. We then add other elements to deform the crystal lattice to make sure that what's left of the system we can work with. And because we've still got 30% of this disordered phase, the other phase, not the precipitate, we shove in things like rhenium and tungsten. Great elements, don't diffuse very fast, get in the way, they just sit there like big blocking elements and kind of tie up dislocations in the other phase. So if the dislocations try to get round the precipitate, they meet rhenium and tungsten. If they try and go through the precipitate, they've got to find a friend. So in terms of stretching these materials, we've tried to find ways of really tying up creep. So the growth that we get of these metals has been really slowed down. We can hang them there with a weight on for a lot longer because we've really over-engineered the alloys. And these slowly diffusing elements are what we use to distort the lattice. And the other one, refining the grain size. Bigger grains make creep harder. Smaller grains make your strength better, bigger grains, so it depends on whether you want strength or creep. We want creep, so we want bigger grains. So what's the best way of getting bigger grains? Well, we get really cocky. Think, well, we could, the first thing you could do is you could take these parts and you could make them directionally solidified. And that's a blade. I put the lights on at the back. If you look at it, it's etched up. You'll see that there's some fairly fine grains in there, if you look closely. So I've chemically etched the surface so you can see the grains. This is a directionally solidified part that we developed in the 1970s, 80s, where we decided that we'd have the really, really long grains. So we'd have them in the direction of maximum stress, so the grain boundaries weren't being pulled apart. So instead of your sugar cube being pulled apart, we'd have long, thin grains, and you pull along the length of them. That made it much stronger. And so we went for directional acidification. I'll let you squint at that.
Yep.
We'll stick them on the table at the end in better lighting, and you can probably have a better view of it. So then what we said was, well, if we get rid of all of the grain boundaries, it's a single crystal. There's no grain boundaries to creep. What a fantastic idea. So you've got single crystal. This is all one grain, this component. 6 times 10 to the 24 atoms, for those of you that want to count them. And you kind of have these, how many atoms is it the number of stones on the beach, or, coins? It's about the same number of stars in the universe, so that didn't help me either. I've still not got an idea. I still can't picture 6 times 10 to the 24 atoms. And it is, I've etched this one up, it is absolutely the most boring blade to look at etched, because etching reveals the grain boundaries. There are none. So, good luck with that. I'm going to pass this one at this end. And you can find out there's absolutely nothing to look at there. So, we went for single crystal. So we have really taken any kind of opportunity. We had the metallurgist kind of guidebook to make strong alloys, and we have done the extreme. We've thrown the kitchen sink at them and made it ridiculously hard for ourselves, but we've done it. What that means is that we've gone from wrought alloys, standard forgings, equiax cast, just pouring it in a metal, in a mould, letting it solidify, directional solidification, and then single crystal casting. Each time giving us a few degrees more of temperature capability that we've squeezed into the engine. And the rest is down to cooling and coating. So we've made these things really, really complex. To give you some idea of what that looked like, I talk about creep, and I've talked about it. That Rolls Royce ran an engine. That's actually one of the blades from the engine, RJ500. We ran it to see what happened. So we ran half a set in equiax, half a set in single crystal, to see what happened. And the equiax one is the longer one. So the one with lots of different grains in all orientations, actually stretched longer over the duration of the test. The single crystal one kept its shape. I can pass it around. It's just, it's a turbo blade. But you can see how that's improved over the generations of material. We've got more of that ski jump of that ramp up because we've engineered the alloys, and we've got that drop off, which has given them a much stronger material at higher temperatures. But to do this, we've thrown the kitchen sink at it. Anything in green, iron, we started off with some iron in the early alloys, we've kind of taken that out. But things we've thrown in: titanium, chrome, niobium, molybdenum, tantalum, tungsten, rhenium, ruthenium, cobalt, nickel, aluminium. We've thrown the kitchen sink at it. The blue ones, boron, carbon, zircon, hafnium, they're all in there to strengthen grain boundaries. So actually we've kind of put them in and then taken them back out again over the generations of turbine alloys. The red ones, they kill your alloy. You get some of those in there and you drop strength. So those are the ones we avoid. The red ones avoid, green ones put in. There's a pretty good spread of elements to put in. And it's not like we put 1 or 2 in, we'll put 8 in, just for good measure. And the reason that we kind of picked those is if you say that the red line is about your nickel-3 aluminium phase melting point, aluminium's in there because we need that precipitate. We need the aluminium to start getting that coherent precipitate. Everything else we've picked has been some of the highest melting point materials we can get. The only one we're really missing is diamond. I'm sure if we could, we would, but we haven't worked out how to do that yet. But we will pick all the other elements we've picked from the high melting point range. They're also some of the densest materials you can possibly get as well. So we don't help ourselves, but those are the elements that we chuck into superalloys. So we've gone for high melting point materials, driving up the melting point of the alloy, so we get that temperature capability. Some of these are really expensive as well. To give you an idea of the composition, a standard single crystal, the ones I've passed around the coated blades that will pass around, CMS84, standard single crystal turbine blade for high pressure turbines. That shows what's in there in terms of weight percent, 3% rhenium, 6.5 chrome, you can see it on there. Density just under 9 grams per cc. So we have thrown just about everything at it. That's mostly because every time we put something in, we actually, oh, that's not so good long term. So we don't want a load of aluminium. So we replace aluminium with titanium and tantalum. Oh yeah, but that gives us issues around castability, and it gives us issues with... So to compensate for the issues that we get, we chuck in something else to compensate. So a bit of chrome goes in there for oxidation, because we take... Aluminium is really good for oxidation resistance, but we're taking it out. So slip in a bit of chrome. Oh yeah, but that's not good for castability. So let's stick some cobalt in there to come... Every time we think there is no element that's really, really good for everything. So we're always compensating for its deficiencies by chucking in something else. To the point where we've probably got to as far as we can. You look at those elements though, in terms of weight percent, CMSX4 plotters a bar chart. Weight percent, mostly nickel. Atomic percent, nickel. The rhenium starts to really stand out between atomic and weight because it's really, really dense. But look at the cost. Rhenium is really, really expensive. 3% rhenium is about, what's that, 70%, nearly 70% of the cost of the alloy. This alloy costs about the same price as silver. It always amazes me. If we wanted a gas turbine that looked really nice, we could make it in silver. It would polish up really well, it would look really nice. It would cost about the same, it just wouldn't work. But it would look really nice. There's another alloy we sit that's even better for creep than this one. What we do is we double the amount of rhenium. Sorry for the colour change. But rhenium in there, that's more like 80% of the cost. This alloy costs twice the price of silver. Because we've chucked in more rhenium, and it's really expensive. As a bit of an anecdote, we tried to reduce the amount of rhenium. It's got a few deleterious effects. It's really good for creep. Isn't great for phase stability. It's not a great material. We decided that the material that would really benefit us was ruthenium. Now, marks out of 10 if you could find that on the periodic table, but we went for ruthenium. And it was really good. The only problem with ruthenium, is that there isn't that much of it knocking around. Nobody really mines ruthenium. It's a byproduct of a byproduct. So you find somebody who's mining for some of the other heavy elements, it comes along as part of the mix, you take it out and you find out there's a spoil heap next to a mine that's got some ruthenium in it. The person that held 80% of the world's supply was a Russian oligarch who was sitting on tons of the stuff and didn't know what to do with it. As soon as Rolls Royce, Pratt & Whitney and GE all said, we're going to stick it in our alloys, the price rocketed. He doesn't quote it on any metals exchange, he deals out of his back garden. Which meant that he controlled the price. And the price went up to about, was it $50,000 a kilo? Yeah, ridiculous price. We all went, thank you very much. And then we all said, I'll walk away. And we did. We all walked away. And the price dropped. Because he didn't have another market, and he just was going to milk what he got. Anecdotally, I think he made a mistake. It'd be better selling it at less of a profit, but having a longer market. Because once we put it on the engines and got it into service, we aren't going to replace that. He's got 30 years of supply. He hit us straight away during the dev engine process, so it gave us the ability to walk away. Interesting marketing philosophy, because we knew what the timescales were, and he didn't. He tried to make his money in the first year. So prices, twice the price of silver. But we've gone for this kind of wacky crystal structure. Precipitates, not 5% like aluminium alloys, we're going for 70%. Narrow channels to stop the dislocations moving. We're going to make it work for optimum compositions, and it looks a bit like that. We've got some really nice photos of it. It looks really pretty. And that we're going to tie and do this, and we're going to make it a single crystal. So the whole crystal structure is all the way through. All those atoms are kind of the same. So how do we make the blades? How are we going to make these things? Joseph Wright of Derby, sorry, coming from where I am, that's kind of topical. It sometimes feels a bit like that on an industrial scale. Investment casting. And we're going to trace it back to about 4000 BC. So this isn't exactly the newest thing we've touched on today. We're going to use a process that's been around for six millennia. And we're going to start, and it's a great process, investment casting. I'm sure that was defined by the banking community. It doesn't actually mean that. If you go to about the fourth definition in the dictionary, investment means to clothe or to cloak. Just like you can get invested in office, and it means you're clothed or cloaked, given the robes of office. So the investment casting is to clothe or to cloak a pattern with a ceramic, remove the pattern, pour the metal in. And investment casting is where we started. The pattern is basically, typically it was beeswax. We don't use beeswax anymore. No bees were harmed in the making of any of the products today. It's commonly used for jewellery, for dentistry, for artwork, and has been through the years. All of the uses over the centuries have been mostly non-industrial kind of product, but artistic stuff. Then we get into the kind of the modern day stuff, somebody decided in 1890 to kind of try for dentistry. So make wax models of teeth, then they cast them up in a little furnace in their own little back room, and they'd make these little teeth bits. And they kind of worked their way through. And they started to use different materials. They started to make these crowns out of different materials. Really good for gold crowns. Really good process. Wax model, stick it in clay, pour it in, pour your gold in, get it out, you've got your gold tooth. The bit that always kind of confuses me, the Austinal labs were basically working on dental materials. Now, a Vitalian, when it came out of there, it was somebody working in a dental lab decided they needed a really high temperature alloy. For reasons that escape me. Curries, yeah. Yeah. But it turned out that it was really, really good for the supercharger buckets of the aircraft during the Second World War. So why you need a dental alloy that could take hundreds of degrees? But anyway, that's where it came from. And we actually then looked at this. It came across to Rolls Royce from America. We started making the pieces here during the war. And then we've gone for vacuum casting. It's been developed out. So it used to be that document, great document, Rolls Royce has still got it. And there's photos in there of how this process was brought across from America and was brought in and set up in the shadow labs in Glasgow, Hillingdon, before it was moved down south later on after the war. So there's all these photos of gentlemen in white lab coats wearing the safety flat caps, pouring metal, which doesn't, it's an interesting document. I wouldn't say health and safety was their primary concern at the time. But anyway, we've gone all the way through to single crystal casting in the 1980s, and that's where it was developed. So we've pushed it all the way through. But what we need is, we need to make sure that we can actually get a hole in the middle of these blades. I'm going to pass this round. At 80% certain it'll come back in one piece. It's ceramic, it's not very strong. So it might not make your own. Don't worry, I have another one. Basically, we're going to make a ceramic model of the hole we want in the turbine blade. So we want a hole at the end, so we're going to have to make it in ceramic and again put it in a mould to make sure the metal doesn't fill the space that's got the ceramic in it, if that makes sense. So that's a solid model of a hole. So we're going to start with that. It's silica. It's not an ideal material. It's not aluminum, which would be really good. It's silica, and we injection mould it into steel dies and make some fairly complex shapes. Because actually, the more complex we can make those passages, the more efficiently we use the cooling air. When we pass the air around, we really use it efficiently. We burn out the binder, we end up with the core as you see it there, and that can be taken and we can pass that into the rest of the process. A bit of buttering, a bit of tidying up, and we basically end up with that lovely ceramic piece. We'll then place that in a wax die, close the die up, inject wax around it. I won't pass this around because I know it won't survive, even when it's afterwards. That's basically a turbine blade wax model thereof. So that's a turbine blade, got the core already inside it. I've lost a bit off the trailing edge already. But that is effectively a wax model of the turbine blade. So I've now made exactly what I want, a wax with a ceramic core on the inside. Once I've got that, and it's a paste wax, 70 degrees C, and we can inject it and make the parts. We'll inspect them, and we do inspect every blade to make sure that the cores survive, the wax is the right shape, and every part gets inspected. Well then, the core itself is silica. We need it to be silica, otherwise we'll never be able to remove it chemically afterwards. It has to be a ceramic that we can attack with a chemical. Otherwise, there's no hole. So we use silica, but silica's got a bit of a problem. It goes through a really weak phase before we cast it. So actually what we really try to do is cast and hold it in place. So you walk into an investment foundry, and despite the cost of all the alloys, the only thing we keep in a safe are the pins that we use to hold this core in place while it's going through its weak stage, which are made of platinum. We keep the reels cost about £250,000 each. Each one lives in a safe. Interestingly, when we last did a re-layout of the precision foundry in Derby, we had to move the P-pinning, the platinum pinning machines, which looks like here. We were going to move it on a weekend. We moved on a Saturday. Do you know how many volunteers we got to sweep up the floor and tidy up where the machine used to be? I think everybody in the wax room wanted to volunteer to help move the machines, because you could sweep up a few grams worth of platinum that had fallen on the floor. But we basically use platinum not because it's got any particular properties, apart from the fact when superalloy hits it, it dissolves. It's like boiling water on sugar, it just dissolves. So platinum dissolves into the superalloy, and you end up with a witness afterwards that's superalloy, but it doesn't leave a kind of a platinum. It's not a concentration of platinum, which will be weaker. It just dissolves into the material. And the alloys are actually certified to have a small trace element amount of platinum in them, because we know we're going to dissolve it in. So it dissolves, disappears, that's fine. Then we're going to stick these parts together, and there's Belinda there assembling up a nozzle guide vane. There's some turbine blades on the top one, and we're going to make that wax assembly. We use different coloured waxes because they've got different melting points. The red one happens to melt at a slightly lower temperature, which allows it to flow out before the green one, and allows us to control the flow of getting this outside of the shell. Really useful, because we're going to coat this up in a minute. Let's show the photos of coating up. We're going to dip it in a kind of a wet slurry, which is a silica sol, kind of a liquid, a bit of a, I don't know what it really looks like, a very runny kind of bread mix. It's kind of very sloppy. And you dip it in there and you pull it out and you let it drain. Then you're going to stick it into the sanders, which you can see at the back of the lower photo. And they just drop bits of ceramic on, very fine bits of ceramic, 0.2 millimetre, 0.5 millimetre, those kind of sizes. And because it's wet, it's like running up a beach out of the sea. You run up a beach with your feet wet, you get covered in sand. We use exactly the same principle here. We take it wet, stick it into the sander, rotate it round, and the sand sticks to the wet surface. And we then stick it on a dryer, send it away for a couple of hours, control the temperature, control the humidity, dry it out, come back and do it all over again. And we do this depending on the size of the component. So a little helicopter blade like this, we probably do that 5 or 6 times. Larger blades, industrial gas turbine, could be 20 times. Normal turbine blade, the type of passed around, is going to be somewhere in the region of 8 times top. The primary coat, the first one, the one the metal sees, best quality. Thickest slurry, finest sand, that's the one that gives you the surface finish. After that, slightly more runny slurry, thicker sand, we're just trying to build up bulk and strength. But then we're going to want to get the wax out. So we're going to dry it for 24 hours, it's still not particularly strong, and we're going to stick it in a machine that looks like the one at the top there. We could use a furnace, but we can't heat it up slowly to melt the wax out. Although it melts at 70 degrees C, if we heated it up slowly, the wax would expand. The shell isn't very strong, it would expand and blow apart, and we'd end up with crumbs in the bottom of the furnace. We've tried it. Yeah, that wasn't one of the more successful ideas. So what we're going to do is we're going to stick it in this kind of vessel, and we're going to close the door quickly, press the button, and in 4.5 seconds we hit it with 4.5 bar of 180 degrees C superheated steam. High pressure steam, high temperature, and the wax suddenly finds that wax has got a great property. It doesn't conduct heat very well. So actually it melts the surface of the wax before it gets into the bulk and causes it to expand. So it kind of flows off from the surface, and it flows all the way down on the inside of the shell, flows away, and we don't blow the shell up. Neat trick, if you can get away with it. It has to be, we hit it very hard, very quickly. Once you've got the wax out, 800 degrees C, biscuit fire from ceramics industry, biscuit fire, 800 degrees C, gives us enough strength to handle it. And we end up with, on a small furnace, a shell that looks like this. I won't pass this round because this is fragile, but you can come and handle it later. Ceramic, hollow, we've burnt the wax out, we've given it a bisque fire, and so we've got the cores inside there, and that's now ready for casting. So that's what, now, Rolls Royce uses a number of different sizes of furnace. This is a particularly small one. The big ones are about that big, and two reasons. One, I couldn't get it particularly well in the car, and two, I can't carry it either, so I didn't bring one of those. But we'll get, that's got 4 parts on it, the big one's maybe 24 parts, turbo blades, and we'll send those for casting. Now, we can do equiax casting, and that's the polycrystalline one. So we could end up with blades that look like this. This is another etched up polycrystalline one. I'll pass that round. This is actually an old polycrystalline, that's Concorde, HP1 blade. So that's a high pressure turbo blade from Concorde, equiax. So that's that kind of technology. But we could just pour the metal in, let it solidify, and we get that. To give ourselves this single crystal directional solidifier, we want to control how those grains grow. So we're not going to just let it pour the metal in and let it flow and stop. What we're going to do is we're going to withdraw it slowly from the hot part of the furnace to the cold part of the furnace and encourage those crystals to grow from the base. So, I think I've got a bit of a... There you go, that's what the furnace looks like. That mould there sits on a copper cooled chill. And what we do is we take the metal, we dump it into the... We melt it in the top chamber, it pours into the shell, and we leave it in the shell. In that shell, it's still molten. The top chamber of the furnace, well, that middle chamber, is at about 1500 degrees C, give or take. So, the metal is still molten. The alloys melt at 1320, 1360, depending on the alloy. So we're well above the melting point. Apart from where it's gone all the way through the mould, I'll break it myself, and in here we've got a water-cooled copper chill that it sits on. We pop it into the furnace, bayonet fit, water-cooled copper chill. That means that as soon as the metal flows all the way through and hits the bottom, there's a small layer of chill crystals. But that's all there is, sitting on top of the chill. Above that it's molten. Now those chill crystals are any orientation. It's equiax that we don't know which orientation they are or anything. They're just lots and lots of them, thousands of them. But then we start to remove that on the ram, water-cooled ram, hydraulic ram, starts to withdraw. And we start to take it from the hot zone into the cold zone. And as we drop out of the hot zone, we get to the point where the metal starts to want to solidify. Now, great thing about what we're doing, it's always easier to grow a grain than start a new grain. So lots of those crystals that sit at the bottom, we start to encourage them, the top layer of them, to grow as we withdraw. Now, that's the beauty of it. We're going to take those grains. That's what it looks like. We're just going to grow that. That's it. That's the cartoon. That's what it looks like when you start to do a little bit more of an engineering drawing. It's a bit more controlled than it is, and we start to get these crystals to develop. Now, this is what happens. We get this, and we're going to withdraw from the top mould into the bottom mould. Not quite that quickly. It takes a couple of hours, but we're going to move it slowly from the top to the bottom, and we're going to get it to drop in temperature as we do it. What that means is, as we start, at the very bottom, we've got the chill layer sitting on there. This is, imagine the component above that, we just happen to have cut it off. So in there you've got the metal. That top bit is going to be liquid, that's solid. As we withdraw it, these crystals start to grow. Then they hit this kind of selector, this kind of twisty pigtail. Now, it just so happens that the orientation of the crystal that we want, vertical, is the one that grows the fastest. We looked out there. So we're going to grow these crystals really quickly, like 9 inches an hour, so not very quick at all. But the crystal orientation that grows the quickest grows up, grows sideways, and kills off all of the other orientations. So by the time you get about 5 millimetres into growth, the only crystal orientation you've got has got the vertical orientation that we want. We just don't know, we've got lots of them, we just don't control the rotation, we don't need to in most cases. There are ways of doing it. Then we get to the pigtail, and that selects out one of those grains. And it's just a mechanical selector. Because as a load of grains go in at the bottom, through the choke at the bottom, then one of them grows up and stops its mates growing into the kind of the angled tube. So you get this angled tube and they all grow past it, and one of them just grows past the edge, and the others can't go past it, so one of them goes up and grows sideways, and actually goes round. And in 3D, a pigtail is a mechanical selector for single crystal. A couple of edge parts if you can squint at them. Send that one that way. And then we'll run the video. Just be careful, there's a couple of birds on one of them. Right, so we're going to grow like that. All the crystals are now the same orientation, just lots of them. Then we're going to hit the single crystal selector and pop. One grain makes it through, blocks off all its mates, gets to the top. Single crystal pops out. We then take it through that kind of delta that spreads it out, and we grow that carefully through the whole component. So we've selected one grain, and we've encouraged it to grow all the way through to the top. Now, as I say, a couple of hours to do that, 3.5, depending on the blade size. So we get this option. We've got this optionality of how we do it. We can either do equiax. That kind of didn't show very well. But we can do directional silification, or we can do single crystal. And we can grow all of these components and actually make a lot of different things. You know, all of the blades are by the same process. Once we've got them, the shell's looking a bit sorry by this time. It's done a couple of 3 hours, 2 or 3 hours, and it's kind of a bit past its sell-by date. So we're going to knock the shell off, we're going to take it, we're going to chemically remove the core and end up with the component. And so we end up with something that looks a bit blocky, but you can kind of see, we can take the core out and we end up with those kind of passages on the inside. So we've gone all the way through that process and we've ended up with a component that's a single crystal. This is all single crystals. I'll let you come up. So it doesn't really matter whether we're making something this big, that's an IP turbine blade in that really expensive alloy, something that big, or an industrial gas turbine. So helicopter blade, simple turbine blade. We can go through the scales. Exactly the same process. To the point where Bristol used to be known as the military facility, Derby was known as the civil facility in Rolls Royce, but the foundries actually didn't focus on that. They actually focused on variations on the process. Bristol used to be equiax. It's now very, very large single crystal parts. Derby, smaller single crystal parts, Rotherham, same size as Derby. And actually, it doesn't matter where it is, what we're making, whether it's the military parts, civil parts, they all go through the same foundry. Because actually, it's not what the part does in the what the engine does, it's actually the process that we use. It makes no difference. So we've got that. I mean, that's bizjet sized. So there's all sorts of different sizes that we knock around with. So we end up with that. We're going to core leach, take the core out. Then we're going to overaddress it, inspect it, heat treat it. And every part goes through every inspection hole. It has to be stamped off. Because if we get a failure in service, we have to make sure that we can go back through the records and determine who did what to which part when. And we've done this. You get a failure, we'll go back and we say, well, you stamped that part off. Do you remember anything about it? And we'll chase it round. And it's all on paper still, by the way. Because we've tried to move away from paper, but can anybody think of any other medium that survived the last few thousand years? We all thought that CDs were good. There are some exceptions for some bits, but the only bit that we've got away with is X-ray. When we actually X-ray every part, we are now allowed to do digital X-ray because the old silver plate X-rays, if you keep them for enough years, they become a fire hazard. And there was a couple of foundries globally that burnt down because their X-ray store went up first. So actually, we've been allowed to save digital X-rays, the FAA have allowed it, but only if we write the file to 2 servers and save both servers in a secure store when we've done. So actually, they're really fussy about how we keep records. So anyway, we've been through the process. We start with the core. We try and make that whole. We then wax, when it was wax, we assemble it, we shell it, de-wax it, pre-fire it, prep the cast, we cast it, take it out, inspect it, send it off for machining. And then when we've done all of that and we've machined it, we'll then go and stick a coating on it. Typical barrier coating. It's oxygen transparent, so it doesn't protect from oxygen very much. but it's partially stabilised zirconia that we grow on the surface, and that's 200 microns thick, and will reduce the temperature by 200 degrees C. There's a whole technology lecture in what we do in the coatings, but we'll coat every single crystal blade like that. And so we end up with these components where we've got lots of things going on to make sure that at the end of the day, everything survives. And, you know, understanding why these things fail is often we'll lose the thermal barrier coat and we'll burn through the blade, and that's why things get taken off wing after 10 million flying miles. It tends to be things like that, the loss of the barrier coats, that actually mean that we're going to replace after however many, 5,000 flights. So, turbine blades go through exactly what these blades have to go through. 300 degrees C above their melting point, 27 tons of load, a load of heat, 900 horsepower they have to remove to keep the engine running, and those are the requirements. And that is the requirements that we have to do, and that's how we meet those requirements. Investment cast, single crystal casting with coating on a cool turbine component. And that was a whistle-stop tour through turbine components. I'm sorry for the technology in the middle. Any questions?
From a non-engineer. Given that you've got a crystalline alloy, can you recycle any of this? If you take components off, can you reuse your alloy?
Yes. This is where it gets really good. For years, when we do a casting, all of this stuff we don't use. All of the bits I've handed around there, the pigtails and stuff, we don't use. We segregate those alloys, we remelt them, well, they go back to the alloy supplier. The business case is such that we segregate them, we send them back, they're cleaned up, they go back, they go around the loop. We've been doing that for 2-3 decades. And basically we ship back to the alloy supplier free, because actually then that comes off the cost of the next batch that comes back in. Because if you charge them to take your scrap away, then they charge you more for the privilege of charging us in anyway. So we've worked out the economics of it, and it does come round. We also look at what we call engine room solids, and that's blades out of an engine that we need to get back. We would really, can we reuse those? Yes, we can. Take the coatings off, clean them up, engine room solids can get remelted down. As a complete aside, we've been doing this for years. There isn't a problem with it. We're certified up to 100% revert. We can't use 100% revert because that means we'd have to recycle all of the bits all of the time. And actually, we need some to get into service and fly. So it's at the moment, with the increase in flight, it's about 50-50. I approached the NHS and said, what do you do with it?
That's what I do.
Right. What do you do with body parts when you take them back out? Well, we bury them as clinical waste. That's good. And I was told, well, you can't remelt them because it won't have the same properties. Okay, nobody has an implant and runs at 1600 degrees C with 27 tons off the end of their leg because they've had a hip replacement. There is no reason we can recycle aerospace alloys. There's no reason we couldn't reprocess. And I'm not talking about taking it out and cleaning it. I'm taking it out, remelt, reuse, round the loop. We could do exactly the same thing with medical implants. That's a complete aside, by the way. I've got a PhD student looking at it.
Can you explain how the single crystal process was developed? Was it an accidental discovery, or did somebody work out if you used a pigtail, you could grow a single crystal?
Right. Bridgman developed the furnace for doing DS casting back in the 1930s, got a patent on it in America, and that worked really well. So that was where that came in. The whole selection process came out of America. Pratt & Whitney developed it. They wanted to see if they could do it, and they had all sorts of different square shapes and round shapes. They fiddled around with the pigtail till it worked. So it was a bit empirical, but I think they knew that if they could get a blocking system on an angled tube, in 2D it's effectively an angled tube and the last crystal past the guard blocks the others kind of thing. So they knew theoretically it was possible. It was just fiddling around and making sure it worked in the furnace.
So did they not patent it?
Yes, they did.
So Rolls
Not well.
Royce had to pay for it.
It wasn't done well.
Good. The cooling of the fan is obviously important. I've noticed on the moulds, got these little slots to increase the surface area. Is that a difficult process to try and like golf ball the inside to
Right, we
get
don't
the surface area?
We do try and increase the surface area. We don't golf ball the inside, but we do put trip strips in there to get the turbulent air, and that's the way we do it at the moment. We're looking at lattice configurations.
Will you comb it inside?
Sorry,
Will you comb it to give a big surface area?
we could try, but casting that's quite difficult, especially if you want single crystal. Yeah, trying to get liquid metal penetration into anything below about 0.3 of a millimetre is quite tricky. We think we've got ways of doing it, but just the viscosity of the liquid at those temperatures and trying to get it to penetrate into a thin channel is quite tough. Yeah.
Increasing grain size in order to improve creep resistance. That I always thought it the other way around, because if you want to increase the strength of a metal or a steel,
Yep.
The understanding is that the smaller the grain, the better, because the crack length is far greater.
Yes.
And
Hall
they
Petch.
fail because of a
Yeah.
crack right the way through.
Yeah. Hall Petch says if you want increased strength, so tensile strength, you go to finer grains.
Yeah.
If you want high creep, you go to bigger grains. So depending on whether we want strength or creep strength, tensile strength or creep strength, because they're two different mechanisms, we have to pick our structure. And actually, it's creep strength that dominates in this application. Hence we go for single crystal. In other parts of the engine, it's tensile strength. We go for fine grains. But for the turbine blading, it's creep.
One last question.
Yeah.
Just thank you, Paul, for your talk today. As an instructor here for 20 years ago, it took me about a week to explain what you've done tonight, so well done.
I didn't say it done well.
Yeah, I was just kidding. But 20 years ago, we were discussing then about, because obviously, like you said, the HP turbine being the limiting factor in the engine, etc., etc. But the introduction of ceramic blades. Now, I understand that they can be quite fragile, but they were very resistant to creep. Has that progressed anywhere?
No.
No.
Well, GE are talking about ceramic matrix composites. They put out a publishing document probably about 10 years ago now that said that the Gen X would have seal segs, nozzle guide vanes and turbine blades in ceramic matrix composites. They've done the seal segs. Because they don't rotate, they're lower stressed, you can do that. The problem with the turbine blade is it rotates. And as soon as it rotates and you want a fairly intricate shape, you've got a problem. Straight ceramics, if you wanted to make a ceramic, you're probably you'd say alumina, which gives you up into 2000s, but if you, degree C in terms of capability. But if you want to actually make it and stick it all the bits of alumina together, you need a glassy phase that probably has a temperature limit of about 1700 degrees C. So you're now sat with the fact that to get it to process it, you're stuck at 1700 degrees C limit on your glassy phase. So okay, so we're now at 1600, I get to 1700. So if I want to cool it and make it better, then I've got to have a ceramic with holes in. But ceramics doesn't conduct heat as well, so I can't take the heat out as fast. So I end up in a thermodynamic nightmare of having a brittle blade that I can't cool, that has about the same temperature capability as metal. So apart from it being slightly less dense, I haven't actually made any change to the engine. And that's roughly where we are.
Yeah.
Any of those, if we could break that cycle, I could see us going on a storm. But we haven't done that in the last 30, 40 years.
Thank you.
Thank you. I am not going to try to summarise tonight. That would be madness. I'm sure we have all got our favourite few facts. The 650 degrees cooling air, the use of superheated steam to melt out wax, the fact that each of those blades takes out about the same power as a Formula 1 engine, the fact that you can build the engine out of silver and it wouldn't actually cost any more than it currently does. All absolutely fascinating. I said earlier that we would try to make these lectures, this June lecture, STEM or rotorcraft related. I think we've hit or Paul has hit the STEM nail firmly on the head tonight. The science is there, the technology was fascinating, the engineering was all the way through it, and thank you because you saved us from the maths. We like the maths, but maybe it's a little bit late in the evening for the maths, but absolutely hit it square on the head. So thank you for that. I think the inaugural Chris Hughes lecture has been an absolute treat. Thank you very much. I'd like to invite you.